Hello everyone. So we are here on day 2 of our project session, and on day 1 we did understood the basics of data, the disease, that means domain knowledge we gathered, what we want to do, that's what we discussed, and accordingly we were having images, skin cancer images we were having, two categories, benign and malignant we were having, and we started our coding. That's what I'm showing you right now. Okay, and three models I have used yesterday, and I got success on all the three. Okay, and I'm going to explore a model more on the data. So malignant benign directory path, I loaded the image path in this code, and created a data frame will help us in better understanding of what data we do, and we can apply methodology on this data frame. So head, tail, shape, columns, everything is clear. No duplicates and no null values. Unique, we are having malignant and the benign. Value counts, benign are more than the malignant. I have drawn count plot and the pie plot for the images numbers. Okay, and then I have shown five images from each and every folder, benign and the malignant. Okay, random oversampler I used to sample my data, because benign are more, malignant are less. So let's make both equal. So I performed oversampling. Oversampling, a class which is having less uh, values number. Okay, so that should be increased. Minority class should be made equal to the majority. So this is my data frame, new data frame, df resampled. Here I am having equal numbers. Okay, and then I have used my libraries, especially TensorFlow, for pre-processing and to have the convolution layers and all these things. Okay, and then here I separated my data, split my data into training, testing, and the validation. That's what I did. Okay, and then I performed some pre-processing over my data, and I suggested you that you should also, in pre-processing, kindly apply some transformations, add rotation, add horizontal flip, vertical flip, kindly add. Okay, with small numbers only, but kindly add. Here I haven't added. Whatever be the images I am available with, I am just performing scaling, that means normalization, dividing by 255. I am having color images, 3 channel. Okay, so that's what I'm doing. Binary classification we are performing. We are interpreting it as colored images, RGB. Okay, so I got this result as 10,000 and 1258, 1258. So these 10,000s will be used for training, rest are for testing and the validation. Okay, then I have to use the GPU. I created an architecture, a very simple architecture, but it proved to be very much effective. So just convolution pooling, three blocks I made: block 1, block 2, block 3, increasing the number of filters 32, 64, 128. That's it. And gave my data to this for training purpose, and I got the scores like 90% accuracy for the training and 87% for the testing. That's a good score. So this architecture itself is able to classify the benign and the malignant. Then I proceeded to add some regularization technique in the architecture. Okay, so I used dropout, then regularizer. Okay, again, like this is block 1, this is block 2, this is block 3. I am taking 3 blocks and I'm adding here the regularization technique to prevent overfitting in the model. So what happened is the accuracy which I achieved with training is 83, with validation is also 83. It's going good, not an issue. And the test accuracy is coming like 79. Okay, it's also good. Because of regularization, we have put a restriction to the model, so it will not go beyond. Okay, and early stopping has stopped the model for the further training, and we are here at 79. Okay, then I used another model, that is exception. But when I checked the confusion matrix here, okay, here is an issue. 398 231, that's a big trouble. So it's having misclassification. Anyways, I proceeded with exception. That's one of the pre-trained model, and with the Gaussian noise in combination with your dropout, okay, batch normalization, it helped a lot. In previous data also, this exception architecture. Today I am going to show you the exception architecture also. Okay, so it helped us, and we achieved 90 plus accuracy in training, validation 89. However, with testing, I got the accuracy of 89. Fine. So 89% is a good score with accuracy, with exception model. Then I thought, okay, it's going good. So I used Inception also. There is one more pre-trained model, that is Inception. However, I think I have to use Inception first and then Exception after that, but it doesn't matter. I have also used other models like ResNet, EfficientNet, but they were not giving good scores. So I discarded those models from my code. Since inception and exception are related, so I thought that if exception is giving me good score, why shouldn't I try inception also? So inception V3, we do have inception V4 also. V1, V2 I haven't used. Okay, but yes, there is evidence for V1, V2 also. V3 is successful. Okay, so I use inception V3. Architecture remains the same as we have used in exception. Okay, so just we are having this base model inception, adding Gaussian noise with the same factor 0.25. Everything is same, just change the model. Okay, and then I have compiled my inception model. and then I am training my model. With inception also, I reached till 10 iterations, 10 epoch. Accuracy I got 91 for the training, 86 for validation. Okay. 91 and 86. Well, it's somehow what less than exception. A bit less than the exception. Okay. Then I made the plots. This is how I'm getting the plots. Increase training validation is having some fluctuations. Maybe we have to add some more, that means dropout strength, normalization strength needs to be increased a bit, maybe, because at the end here the difference is 5% in the accuracy. So if I proceed more, it may happen that there will be more fluctuations. Till till here it is okay, then the difference started increasing. So till 10 iterations, okay, don't go beyond. So here these are the plots for accuracy and the loss. When I tested my model, I got the accuracy of 89%, which is equal to the exception. Okay, it's equal to the exception, and I am getting balanced also here. Precision 0.90, malignant 0.88, balanced. This is somehow what balanced scores which I'm getting. I'm happy with that. Okay, kindly check exception. With exception, this is what you are getting. Precision 86, malignant 0.92, 0.93, 0.85. Okay, so precision and recall do have some differences. But here I am having not that much difference. 0.90888790. Because recall is said to be true positive rate. Right now you are doing binary classification. So in binary classification, we have receiver operating characteristics and area under the curve also as evaluation criteria. We do have. And in ROC, AUC curve, we have to focus upon TPR and FPR, true positive rate and false positive rate. Recall is TPR. If recall is increasing, that means TPR is increasing. Okay, that means okay, your model is working good. I am checking in regards to both benign and the malignant. It's more in both. It's not such unbalanced. 0.87, 0.90. It's okay. F1 score is same for both. 0.89, 0.89. So it's not only that you have to display the accuracy. It's not only that you have to print a classification report. It's not only that you have to draw the confusion matrix. Let's see the confusion matrix. Here it is. 550, 79, 63, 566. If you compare with the exception, here exception, these are less, these are more. But in inception, I am having somehow what like, okay, this is less in exception, but here I am having more. This is very more in exception. Here I am having less. So just try to reduce both. Okay, just try to reduce both. However, this got increased, this got decreased. These are false predictions on the diagonal. These are true predictions. Okay, so anyhow, exception and inception both are like comparative models which I got as a result. Then it has been asked to me that, sir, can you perform the prediction? You got a trained model. Okay, so I am having this model, inception model, trained model. Okay, this CNN model, inception one, it's trained now. It's ready to perform the prediction. I can do that. So here I took an image from the test data, malignant image from the test data I took. Then I called predict image method. In the predict image method, I need to take my model, that is inception model. I need to take the image path, and first I need to pre-process the image. So here I am calling another method, and this is the method for pre-processing, because you have to convert this image into 224 size. That is the first step. Second step is you need to convert image into array, and then you have to divide it by 255. That is a normalization. That's what you have did with the initial images of your data sets. So whatever you have done with your data set, you have to apply same thing with, if you want to perform the prediction, you have to apply same thing with the image. So I performed the pre-processing, and then the pre-processed image is given for the prediction here, and whatever be the prediction I got, I have saved its value here in the prediction. Then if the prediction is greater than equal to zero point 0.5, malignant, else benign. The result which I got is malignant, 0.81 confidence. Okay, so you can upload any image and you can make a model to predict. That's what you can do. Okay, so I got the result as malignant. Let me check the okay. That's malignant image only, but I gave this from test data. You can see whatever so far I have performed, that I did on train data. In my data set, I do have train folder and test folder. Whatever I did performed, I did it on train folder. I trained my model on this folder only. Test was unknown to my model. So I pick a malignant image from the test folder. I pasted the path here and asked my model to predict. And it gave me the correct prediction, malignant, 0.81 confidence score. Okay, so here we did tested our model. I have already shared the code with you. Okay, and I request that at least we are now at project number 9. I request kindly write something that what you have learned so far till this project. No comments I have seen, nothing. So this code is available. It's open, it's public code. I made it public. You can run and you can do the changes and you can check the scores. Then there is one more question asked to me. There is one more question asked to me, that what is the performance? That means if you evaluate the, okay, we have done the evaluation, but if you compare the evaluation, okay, if you do compare the evaluation, so four models we have applied: CNN model, CNN with regularization, exception model, and inception model. Four models we have applied. Okay, so CNN model, these are the scores: precision, recall, F1 score for benign and the malignant, overall accuracy is this, and average scores are this. For CNN model with regularization, these are the scores. So adding regularization negatively impacted the performance. That's what happened. As also we have seen, the performance is reduced. Okay, the performance is reduced with the regularization. That means model was not overfitting. The CNN model was not overfitting. The perform, but instead of that, we our from our side only we applied regularization, and the performance degraded, especially for Benning class. There is a sharp decline in the recall. Remember, recall is very much important. TPR, it is true positive rate. So TP upon TP plus FN, that is recall. True positive upon true positive plus false negative, that is recall. And it should have to be increased for the correct classification. So I'm getting recall as 0.63. That is very less. Malignant class benefits from improved recall, but at the cost of reduced precision. Its precision is reduced. Okay, and recall is increased. Overall, the accuracy and FN scores dropped to 79%. The potential imbalance. That is what I am saying. Focus upon confusion metrics and classification report. Confusion metrics, it's okay. Classification report will tell about these terms. Okay, so we have to focus upon them. There should not be imbalancing in the class predictions. Don't be happy just by accuracy 70, 80 plus or 90 plus. No, you have to check the balancing also here. In exception model, high precision, high recall for Benning and the malignant. Accuracy 89%, balanced FN score, good generalization. Yes, thumbs up to the model. Clearly improvement from CNN and regularized CNN. With Inception, Inception also performs well like exception. 89% accuracy, clearly equal precision, equal recall, equal FN score. That's what I am happy. This model strikes a good balance between Benning and the malignant detection. So you have, it's not like classifications are over. No, you have to see the balance between the scores. Precision 0.9, precision 0.88, recall 8790. Not too much difference. F1 score is same for both. Good. Overall accuracy is 0.89. Okay, so the conclusion says that CNN with regularization struggled. We are not going to use CNN with regularization. CNN simple is okay, but CNN with regularization is struggling. Exception and Inception performed best, 89%. Exception and Inception performance is very close. Now the question is, sir, which one to select? That is a question. Inception or exception? Which one to select? See, both are very close. Either of the model can be used. Either of the model can be used depending upon computational complexity. Okay, and here are my all the scores, and I did performed the comparative analysis of it. This is the comparison. Okay, that's the comparison. Okay, and I think I added one more thing. Here it is. There was a question asked to me, sir, how much time inferencing, how much time the model will take? So I added in the code that thing, time. So process the image. This is the start time, and this is the end time. In between, I'm putting model dot predict. So if you want to know how much time a model takes to predict, the question yesterday was asked to me, sir, kindly tell me the inference time. So I can use a library called as time. So this is the starting time, this is the ending time. In between I am writing model dot protect. So it took only 0.077 seconds, not 1 second also. Fraction of seconds. In a fraction of seconds, this much quick a model is. In fraction of seconds, it gave me an answer. Okay, so if you want to calculate the inference time also, you got it. Okay, so I got two best models, four models I used, I compared, and inception and the exception gave us 89% score. And this is the comparative plot for all the evaluations, precision, recall, F1 score, okay, along with the accuracy. Okay, so that's what you can use for your research and project purpose. This is the complete project. Now, I need to share my entire screen to have a discussion over the pre-trained models which we have used. Apart from them, other models, that means the basic models also I have included. I referred to you this website, OpenGenius. Okay, this is the website I have referred. Okay, so the things got started from the year like 2000 when the CNN came into the picture, no? When convolution neural network came into the picture. So things get started from 2015. So CNN came prior, okay, not from 2015, it came prior. But till 2015 to 2024, there are many changes. There are many architectures which came. So initial architecture was LeNet, then LXNet. So it do have only three layers. Then it is having five layers. So if you want to learn about computer vision, it is mandatory for you to first go through these architectures. So in Lenet we are having CNN, okay, convolution, convolution, convolution. Three convolution layers we have put. In AlexNet we put five convolution. Okay, so how we perform the combination? Convolution pooling, convolution pooling, convolution pooling. Okay, I can put same here. Okay, so one is feature extraction and is another is reduction, dimensionality reduction, pooling. So these two architecture were basic, Linux, LXNet. Then there is a list of pre-trained architectures. I am showing you here on OpenGenius is VGG16, Visual Geometry Group. It's a full form, Visual Geometry Group. We are having VGG11, VGG13 also, I guess. 16 we are having, 19 we are having. So initially, now what happened? Acha, one more thing. During that time, there was a competition held, and in competition, ImageNet data was taken and it was asked to perform classification. So at that time only, these architectures were proved to be good ones. They have achieved good accuracy. That time only. You very well know ImageNet data is a big, okay, it's a lot of collection of different categories, classes of images. That time only these architectures proved to be better. Okay, and there are many things. I request you to kindly read about Lenet, AlexNet, ImageNet, what happened in that particular year, what competition was being organized. Okay, so that's what kindly study. So at that particular time, we were having sequential arrangement. sequential arrangement of layers. That means convolution, then convolution, then convolution, then convolution, then convolution, like this. But there is an issue. As I told, convolution is a feature extraction technique. We are following pooling also. So the image size get reduced. Image size get reduced by applying sequential convolution. We are in okay. We are at risk. Are you diminishing the size of your image? If you perform this thing in a sequence, obviously from 224 you will reduce to 1 1. What are you doing? You know that this is your image matrix, this is your kernel or the filter matrix. How it operate also I have shown to you. That is called as trading. Okay, so obviously your size of image is going to down. So sequential arrangement is complicated. Therefore, okay, in VGG16 we are having sequential arrangement only, 16 layers. Okay, VGG16 consists of 16 convolution layer, similar to LXNet. 3 cross 3 convolutions. So 3 cross 3 filter. Size of the filter is 3 cross 3. 16 convolution we are having. 138 million parameters. Transfer learning can be achieved by VGG. Here you can see architecture, convolution, then convolution, 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 then देखो convolution, convolution, pooling, convolution, convolution, pooling, convolution, 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 pooling, like this. So 16 layers in CNN, sequential. Here it's mentioned. So we can use this architecture also for many. Like, it's a pre-trained no? Over image and data. We can use it for classification, but I haven't used because of our existing. It failed. You can try. Our existing problem statement, it failed. Similarly, just like this VGG16, we are having VGG19. Same. VGG16, we are having VGG19. Only the thing is plus 3 convolution layer more added. So it become VGG19. Okay. That's the only difference between these two. Sequential in nature. Okay. But these are traditional like models. When we proceeded ahead, these models gave an issue. Again, diminishing. Then Inception came. Inception. In Inception, we we do have Inception V1. We have V2 also. But you can see there is a change in architecture. In Inception V1, see, when deep multiple layers are used, in the model, it results in overfitting of the data. To avoid the happening, the Inception V1 model uses idea of multiple filter of different sizes of on the same level. That means it is using multiple filters of different sizes. How? It is using 1 cross 1, 3 cross 3, 5 cross 5, 3 cross 3. Such kind of filters it is using. What does it mean? You can see here. 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3. Such kind of filters it is using. Different. You can see the size of filters. Different. That's what we use in our architecture. What we write? Model dot add convolution 2D 32, then 3 cross 3. What is this 3 cross 3? That is the size of 32 filters. I am having 32 filters, they are having size 3 cross 3. But Inception is saying that no, I am not going to use 3 cross 3, same size. I will be using 1 cross 1, 3 cross 3, 5 cross 5, like this. Okay, we don't use higher filters, no. Very rare. The mostly used are these. And also we take odd, not even, odd size filters. Everything is being done mathematically. These are the proved models, pre-trained models. So Inception is saying, okay, we are not going to use these as same 3 cross 3. We are going to use them as different size filters. Okay. So you can see previous layer, then 1 cross 1, 3 cross 3, 5 cross 5, 3 cross 3. And then whatever be the result I'm getting, concatenation. That's what happened at V1, Inception V1. Okay. And yeah, Inception V1 is also called as naive form. One of the drawback of the naive form that even 5 cross 5 convolution is computationally pretty expensive. It is time consuming. So to overcome, the authors added 1 cross 1 convolution before each convolution layer. That means add 1 cross 1. Okay, add 1 cross 1 before every layer. Before 3 cross 3, add 1 cross 1. Before 5 cross 5, add 1 cross 1. And 1 cross 1 should be there. This is what the authors, the researchers suggested for faster computations. Okay, fine. So this is what happened at V1. Now, what makes the Inception V3 better? One more thing I want to tell. You know, it was like a good thing to have many C convolution layers because it was giving good results. As many as convolution you add, keep on adding, you are getting good results. That was suggested. But issue was diminishing sequentially. If you are taking, then it will diminish. So that's the reason. Now we were having VGG 11. Okay, we started with Lenet, then AlexNet 5, 11, then 13, then 16, then 19. Inception, which you are studying, that might comprise of 42 convolution layers. We are having other pre-trained models, ResNet 50, ResNet 101, ResNet 152. See, the number of convolutions are rising. In exception also, the number of convolutions are more. Only the thing is, okay, they are now using some strategy. Okay, so here you are getting a hint of strategy. The strategy which they are using is, okay, take such kind of convolutions and add 1 cross 1 prior. This is one of the strategy used in the Inception. And what happened in V3? In V3, they told don't take higher 3 cross 3 or 5 cross 5. Kindly perform factorization of them. That means further split them. Instead of making 3 cross 3, it's better you can make 1 cross 3, 3 cross 1. Perform factorization. That's what you can do. So see, in Inception V3, what they did. Here you can see. This is basic module of V1. And now check V3. Okay, here it is. That's what they're doing. N cross 1, 1 cross n. N cross 1, 1 cross n. That's what they are doing. So factorize. This is what they are doing in Inception V3. Instead of 3 cross 3, okay, 1 cross 3, 3 cross 1. So 1 cross 1 we have already applied in Inception V1. Then this 3 cross 3, they split it into 1 cross 3 and 3 cross 1. Again, here in 3 cross 3, they are not using 3 cross 3. Instead, they are using 1 cross 3 and 3 cross 1. So don't use 5 cross 5. They replaced 5 cross 5 with this. Highest they are using 3 cross 3. Now there is no need of using 5 cross 5. Use 1 cross 3 and 3 cross 1. So to reduce the spatial dimension, to reduce the complexity, such kind of matrix, such kind of filters they are using. And also what we can see here is parallelism. Here we can see parallelism. These filters are like, okay, with different spatial. It's looking like, okay, though we are having same thing in convolution. If I write 32, if I write convolution, here no, convolution 32, if I write, so the diagram is made like this. This is how 32 convolutions are taken, like this, all in parallel. Okay, and you have to give your image to the convolution. It will pass through all the filters. Okay, and then you are going to get a result. Okay, so that's what happened in Inception V3. This is the architecture of Inception V3. Factorization. Okay, now I will not talk more about this. It's like fine. The basic concept which I need to talk about Inception is I explained. That is the factorization of the sizes of kernel. Okay, then what happened with exception? This is exception. Deep learning with depth-wise separable convolutions. So exception is the deep convolution neural network architecture that involves depth-wise separable convolution. What does it mean? Exception is also called as extreme version of inception. That means inception has been advanced to exception. Inception you now know. So exception is an advanced of inception. Okay. So in inception network, we use deep neural network only. The name Inceptions probably sound some readers, especially if you are fan of Leonardo DiCaprio or movie director Christopher Nolan. Inception is a movie. It's the name of a movie. I guess Cooper sir might be knowing about this thing. Sir, this is a movie, sir. Inception. Okay. Yes. Okay. So I think you guys might also know about this Inception movie, and he is a famous actor. Okay, and that is released in 2010, no? So it's like old days, 14 years back. Okay, so in general, each neural DNN is considered to extract some feature. Yes, we know that it's a feature extraction technique, CNN. And stacking these layers one above the other is not a great idea. That's what I told. Never use the layer one above the other. That's problematic. So the pre-trained models, what we are using, they give us like some set of CNN layers should be kept in parallel. They are prone to overfitting, and chaining multiple convolution together increase the cost to train the network also. Okay, and another issue is it extract different kind of information. How do we know which information provides the most useful information? So parallelism is very much important. We have seen, see, it's not like that in one day we achieve something. No, it's like every day you are learning something, you are reading something. Parallelism came, na? Here they are telling parallelism and different size. If I do teach transformer architectures also, there too many layers are there, and there also parallelism has been considered. So if you have studied something, you can apply, and that's what we believe in application. It's not like that finishing the YouTube video tutorial. No. Parallelism. Think why parallelism? What is the reason? What spatial dimension you are trying to reduce? What is the issue? That's what they told. Previous layer 1 cross 1, 3 cross 3, 5 cross 3, 3 cross 3 pooling, concatenation of them. Inception module computes multiple different transformation over the same input and finally combine. So that's what inception do. There is one problem. It is still computationally inefficient because of convolutions. So these convolutions not only happen spatially but across the depth. Across the depth. As you keep on adding the convolution, the things get complicated. So each additional, if you add one by one, then one complicated depth increases, computational complexity increases. So the depth is a bottleneck of DNN. If you are increasing the depth, then neural network is going to face an issue. Now the question is how to reduce the depth. They told that okay, it's better to use one cross one convolution across the depth. So the convolution looks like across multiple channels, spatial information, compress it down to lower dimension. That's an idea. Whatever be your dimension is, spatial information, reduce it to lower dimension. So if you are using 30 one cross one filters, the input of the size 128 128 100 with 100 feature map can be compressed into 128 128 30. That's what can be done. So 100 to 30 reduced the depth. Obviously, na, width, height, depth. Okay, this is how you write the configuration of an image: width, height, depth. So, width and the height are for image, depth is for the layer. Okay, so it's saying that if you are having 128, 128, 100, 128 is the width, 128 is the height, and 100 is the depth of a feature map. Let's reduce it to some number, and they have done it like 30. Okay, they have reduced to 30. Due to this reduction, the researchers of Inception module were able to concatenate different layer transformation in parallel. That's what I told. Achieve parallelism. Resulting in DNN was wide and deep. Images shows the difference between inception without one cross one and one with one cross one. So, okay, this is without one cross one, and this is with one cross one. This is inception, and they achieved the success with the inception. We have also seen. In case of exception, that is extreme exception. Okay, that is extreme inception. It takes principle of inception only to extreme level. How? In Inception, one cross one convolutions were used to compress the original input from each of those input spaces. Exception just reverses the system. Instead, it first applied the filter of each depth map and then finally compressed the input using one cross one by applying it to across the depth. What it is doing? It's like this. Inception is reverse of, okay, exception is reverse of inception. Okay, let's see how the things are going on. In Inception, one cross one convolutions were used to compress the original input. See, this is what you got from the previous layer. You applied one cross one. That means you are compressing the input. Then you are applying 3 cross 3. So first you are applying 1 cross 1, then 3 cross 3 and 5 cross 5. But exception is reverse of it. In exception, it is not it first applies the filter on each map and then compress the input space using 1 cross 1 by applying across the tip. Okay, so you can see in the diagram I am having 19, 19, 728. This is the feature map. This is what I am having: width, height and the depth. Okay, so what we are doing: max pooling, then convolution, then ReLU activation function, then convolution, then ReLU activation function. And this is what I am taking convolution 1 cross 1 here to here I am tapping. This is an additional parallel layer which I am using here. Okay, that's what I am taking. Again, same thing. Max pooling, convolution, ReLU separable. Again, 1 cross 1 parallel taking. Again, 1 cross 1 parallel taking this thing. And then, okay, I think, did I studied this thing in an. Okay, I think I should have to go like this. I did study it from below. I think I should have to go like this. This is the size. Entry flow. No? From here, entry starts. There are no arrow signals, arrow signs are made, no? So it's quite confusing. I think they started from here. 299, 299, 3. What I'm getting? 19, 19, 728. So this is the depth, high depth we are getting. So from 299, images are reduced to 1919 and the depth is increased to 728. And then this 728, this is the middle flow. In a middle flow, repeated 8 times, it remains the same. Like I think 1919 728. Here also I'm getting 1919 728. And this is the exit flow. So in exit flow, 1919 728 we are giving. Here also again we are tapping, and that's what they are saying: 2048 dimensional vectors, optional layers, logistic regression, something they are saying. So in exception, what we can understood is the data first go through the entry flow, then in the middle flow, and then in the exit flow. That is what the architecture of exception is. So in the entry flow, that's what you are seeing. This is the entry flow. You are having an image of 299, 299, 3. That means you do have an image of 299 width, 299 height, 3 is the color channel, RGB. So you are having color image. This image is passing from different layers. Here you can see convolution 32, convolution 64. It's quite easy to understand at the moment. Then the output which you are getting, you are passing it to 1 cross 1. Okay, you're tapping it to 1 cross 1. That's what the exception said. Exception said that we are not applying one cross one prior and then giving it to the next. No. Here here the output which you are getting from the previous block, you are separately applying one cross one to it and carry forward it, and internally the same convolution you are applying 128 convolution, whatever with the result you are getting, you are just concatenating it. So it's like a residual connection. Okay, it's like a residual connection. Okay, so you are having an image 299, 299, 3. It's been passed to a convolution block. Okay, it's been passed to the CN block. Whatever be the output you are getting from here, that will be passed to another convolution block. Okay, convolution block, it will be passed. However, you are taking the output, tapping it, you are performing one cross one convolution over it, and then whatever be the result you are getting here, you are getting from here, you are performing the concatenation. This is entry, and it continues. This is continued. So you are separately applying one cross one. That's what the researchers thought. And they proved. We also proved by taking our data that the results are getting tremendous. Other models are struggling. This one is not. So I just want to suggest one thing that Devesh, you have made, I think this person is present or not. Okay, it's not present. So he has made transformer architecture on the wall. Okay, transformer architecture I taught. So he has made transformer architecture on wall, his wall, in his room. There are many architectures. Now, if you are interested in computer vision, this is the architecture. Okay, so here you can see exception is following this entry flow. In between, we are having middle flow. Okay, first entry flow. This will complete. Then this, whatever I am getting from the entry flow, will be given to the middle flow. Entry flow given to the middle flow and then given to the exit flow. So middle flow, I am having 8 similar layers which are mentioned here. 8 similar, like this only. 8 similar, and then this is exit. So again, you can see we are just having a network of convolution only. What's present? Convolution ReLU, convolution ReLU, convolution max pooling. Okay, ReLU, convolution, all these things. Convolution, ReLU, convolution. Okay, everywhere we are having convolution only. So that is what the feature extraction technique. That's how we are extracting the data, information from the images, and we are achieving parallelism. Okay, we are achieving parallelism. Okay, so the data first goes through the entry flow, then it goes through the middle flow, repeating this thing 8 times in the middle flow, and finally go through the exit flow. This is the architecture of exception. It's been trained on 60 NVIDIA K80 GPUs. This frame is given by Google TensorFlow, Google framework, TensorFlow. So Google Brain, these guys were full on. Okay, it's been tested on ImageNet. These are the scores. Exception gave 0.79% accuracy and 0.94 top 5 accuracy. Okay, so it's better than inception also. Not too much difference between inception and exception. 7.8 and 7.9. That's it. Not too much. That's what we have seen in our skin cancer also. Both the models are like compatible only. Okay. And this is the comparison, inception and the exception. Very marginal difference. Exception is achieving a good on margin. Okay. So I have used these algorithms in my project, so I thought that let's talk something about pre-trained models. Okay, though the things are very broad to learn to understand. Okay, however, here by seeing this architecture, at least we got some idea. Okay, so if you are doing research, you can apply these models. I have already took such problem statements: skin cancer. Previously, I took bone fracture. So there are many other problem statements. You can apply these algorithms there, and you can look out for the results what you are getting. Okay, and we can have a comparison. That's what I did. This is the comparative plot, comparative performance of all these models. Okay, fine. All right. I hope this makes a sense. Okay. So thank you, sir. Thank you. Let me stop presenting. Let me stop recording.